Hello YouTube, welcome back. Today what we're going to be talking about is multiplicity and zeros of a polynomial. So last video I discussed about leading coefficients, I discussed about degree and end behavior, all that stuff. And today I'll be just discussing multiplicity and zeros of the polynomial. So let me turn on my pen and let's get on to it. So, zeros of a polynomial. Zeros of a function refers to the x-intercepts. So a zero is basically the x-intercept. These terms can be used the same way. A zero is just an x-intercept. So example 1 says, what are the zeros of the function p of x is equal to this? So by zeros, I mean x-intercepts. And what I'm noticing here is everything is being multiplied into each other. So what I will really have to do is figure out what makes each binomial equal to 0. Because if you remember, if this just becomes 0, then this entire thing, whatever it is, it's all going to be 0. So let's work on finding out the zeros now. So let's first do this over here. So x minus 2 is equal to 0. So what we have to do is add 2 to both sides, so x is equal to 2. So one of the zeros is x equal to 2. Let's do this over here. X plus 3, so whatever makes this binomial equal to 0. So we're going to say x plus 3 is equal to 0. So x is equal to minus 3. That's another 0 right there. And what makes this 0 here? Looks like if x is negative 5, then that means it's 0. So you can say x is equal to negative 5. That's supposed to be an x. I don't know if I can erase it individually, but that's an x right there. And whatever makes this 0, so 4 minus what equals 0? 4 minus 4 is equal to 0. So we can say x is equal to 4. So these would be all your zeros to the polynomial functions. It's whatever makes each binomial 0. And if you plug in these x values, so for example, if you plug in 2, then you're going to get a y value of 0. So let's move on. So it says, state the zeros of the graph function below. So if you remember, zeros are just the x-intercepts. And what I'm noticing here, this is an x-intercept, this is an x-intercept, and this is an x-intercept. So it looks like we have a 0 at minus 3, comma 0, another one at 1, 0, and another one at, looks like 5, 0. So these would be our zeros, or in other words, x-intercepts. You can just, based on looking at the graph, you can deduce that. Let's move on. So now that we have a base foundation of zeros and x-intercepts, let's move on to multiplicity. So multiplicity refers to the exponent on each binomial factor of a polynomial. So if we look at the binomial factor x plus 3 to the power of 3, this would have a multiplicity of 3, because right over here, the exponent says 3, so I'd reread that as a multiplicity of 3 for that binomial. And same thing over here, since this binomial has an exponent of 2, we would say this factor has a multiplicity of 2. So it's really as simple as that. All you have to do for each binomial factor, you just have to look at the exponent, and that'll tell you its multiplicity. So, example 1, it says state the multiplicity of each factor of the polynomial. So I'm going to read from left to right. So what is the exponent on x minus 6? It looks like the exponent is just 1. So we can say this has a multiplicity. I'm just going to write MP for short. Multiplicity of 1. And let's check over here. X plus 2. What power is this raised to? Looks like it's a 4. So we can say multiplicity of 4. And lastly, this x minus 3 binomial here looks like it's raised to the second power. So we can say multiplicity of 2. And there we go. It's as simple as that. Whenever you have a factor down polynomial like this, where all of its terms are binomials multiplied into each other, to figure out the multiplicity, all you have to do is look at the exponent and it'll tell you that. So now that we know what multiplicity is and how to calculate it, let's move on. So let's talk about multiplicity behavior. At an odd multiplicity, the graph crosses the x-axis. So if you have a binomial, let's say you have x minus a, if this number right here is odd, if this exponent is odd, then you're going to have a graph that crosses at the x-axis. So for example, at this point right here, notice how the graph crosses the x-axis. It goes up the straight line above the x-axis. That indicates at this 0 right here, so let me write that in. At this 0, it has an odd multiplicity. So If a graph crosses the x-axis at a 0, then that means it has an odd multiplicity. And same thing for this point right here. Notice how the graph crosses at the x-intercept 1, 0. That means at that point, at that 0, we're going to have a odd multiplicity as well. And same thing for this one. Notice how it crosses the x-axis. We're going to also have an odd multiplicity there. So this polynomial just consists of odd multiplicity on each 0. So yeah, let's move on. So what about for even now? So at an even multiplicity, the graph bounces back and doesn't cross the x-axis. So for an even multiplicity, what I'm referring to is this over here. So let's say we have a factor, in this case, let's say we have the factor x minus a. And if whatever the exponent here is, if it's even, then that means it's not going to cross the x-axis, it's going to reflect back. And we see this behavior right here. Notice how the graph comes down like this, but it does not in fact cross the x-axis at this point, but rather it bounces straight back up. And that means we have an even multiplicity at the point 2, 0. So at the point 2, 0, we have even multiplicity. Even multiplicity. And there we go. That is even and odd multiplicity, basically odd multiplicity at every single 0. If you have an odd multiplicity, that means you're going to cross the x-axis. But if you have an even multiplicity, that means you're going to go bounce back straight back up. Okay, let's move on. So let's talk about multiplicity behavior even more. So now that we've discussed even and odd multiplicity and what they do, how do we actually know what multiplicity number we're dealing with? Because there are many different odd numbers. For example, 1, 3, 5, 7. How do we actually figure out which multiplicity we're dealing with? So a multiplicity of 1 basically means it looks something like this, where the line cleanly crosses the x-axis. So for a multiplicity of 1, nothing's weird going on. You're normally just crossing the x-axis. You can treat it like the x-axis is not even there. It's just crossing through it smoothly like that. So that's for an odd multiplicity of 1. Notice how it's odd. And for a multiplicity of 2, it's a similar thing. Basically, all that's happening is it's cleanly bouncing back. Nothing weird is happening. All the bounces back are clean, and there's no spacing. So that's for a multiplicity of 2. But if we get into multiplicity 3, things get a bit weird. So it doesn't cross the x-axis as smoothly. Notice how there's some kind of like space here that's not cleanly passing through the x-axis. So for a multiplicity of 3, there is a little bit of space here that you have to that identifies it as a multiplicity of 3. So you can say it like that. So instead of multiplicity 1, where it cleanly passes through, we're going to have this little bit of space here like that. So it passes through like that. And a similar logic applies to multiplicity 4. Basically, instead of cleanly bouncing back like this, you're going to be having a little bit of space in the middle here. That space is going to exist, and then you're going to bounce back up. So as you get higher and higher, for example, multiplicity 5, that space becomes more apparent. So yeah, for example, as you get higher into the odd numbers, multiplicity 5, 7, this space in the middle, whatever 0 you're dealing with, it gets larger and the gap increases more and more. And same thing for even numbers. In that case, they'll bounce back. So let's move on. So let's do some examples. For each 0, state the multiplicity. So I'm going to work on this graph first. So I'll go from left to right. So I'm noticing there's a 0 right here. And it looks like this is an even multiplicity because it's bouncing back. So we already know that. And it looks like this will be a multiplicity of just 2, because if a multiplicity 4, if you remember, it looks something like this. It has a little bit of space like that, and then it goes up. But since it's a multiplicity of 2, it'll look something like this, where it cleanly bounces up. So we can say multiplicity of 2. And for this point here, another 0, it looks like it crosses the x-axis pretty cleanly. So we can say it has a multiplicity of 1. So you can say multiplicity of 1. If this graph did something like this over here, where it had a little bit of space and then it went up, then that would mean it would be a multiplicity of 3 or 5, depending on how much space was here. But since the graph cleanly goes up like this, we can say it's just a multiplicity of 1. Okay, perfect. So we move on to the next one. So let's again go left to right. So I'm noticing here, this point right here, looks like it cleanly crosses the x-axis. There's no space. So we can say this has a multiplicity of 1. Multiplicity of 1. because it crossed the x-axis, and that's odd. Let's move on to the next 0. Let's take a look at this. So notice here, there is a bit of space when it crosses the x-axis. It's not clean. It doesn't cross the x-axis cleanly. It doesn't go like this, for example. It's not crossing the x-axis clean. So we can say it has a multiplicity of 3. So we say multiplicity of, say, 3. There we go. Now, let's take a look at this last function over here. It needs a different color. I guess I'll go back to red. Let's go left to right. Look at this 0 first. It looks like it bounces back from the x-axis, so we're dealing with an even multiplicity. And it doesn't bounce back cleanly because there is a little bit of space there. So that means I can deduce it is a multiplicity of 4. So we can say multiplicity of 4. Let's move on to the next point here. Looks like this point does, in fact, bounce back more cleanly. So we are dealing with another even multiplicity here. But in this case, it bounces back a little bit smoother. There's no space in the middle. So we can deduce this is a multiplicity of 4. 2. Multiplicity of 2. Multiplicity of 2. And there we go. That is multiplicity in zeros. I'll be making a practice video on this. We'll be going through some practice problems. So I'll see you then.